what should we determine? We should determine the nature of the semiconductor, that is whether it is p type or n type material. The conductivity is given as 200 ohm inverse meter inverse. We will have to also find out the density and the mobility, the charge carrier density and the mobility of the material. Once we decide whether it is p type or n type, we will put the suffix np or ne here, and of course mu p or mu e here. How can we determine the type of the material? We are given the RH as negative, so we can say that RH is negative. That means the charge carrier concentration is electrons. The majority charge carriers are electrons, and we can have the values here Ne and mu e. That we can say that the nature of the semiconducting material is n type material. And also we can find out Ne using the same equation that we have used earlier, but here we are given RH. So we can have Ne is equal to 1 over RH E, and just substituting the values, 1 over minus 7.5 into 10 raised to minus 5. If you don't use minus here, then it's okay, because we have already determined the type of the material. 7.35 into 7.35 into 10 raised to minus 5, and E is 1.6 into 10 raised to minus 19 coulomb. So we can have as the answer 8.5 into 10 raised to 22 electrons per meter cube. Now how can we find out the mobility? Mobility can be defined as sigma RH. It is electron mobility, so we can have just the value 200 into RH, that is 7.35 into 10 raised to minus 5, and the answer is 14.7 into 10 raised to minus 3 meter square per volt into second. This is the standard unit of mobility, right? We can also have another example of for this Hall effect, but it is of course it is the conductivity that is given, or we can take another one that says that a rectangular plane sheet of the doped Si silicon, it has the dimensions of 1 cm. See the style of asking, 1 cm along y direction and 0.5 cm along z direction. Now it is you have to decide which is the thickness and which is the width. Say hole probes are attached on it on the two surfaces parallel to xz plane. Say if you have this specimen here, say this is the conventional directions x, y and z, right? 1 cm along y direction, so this is 1 cm. 0.5 mm along z direction, so this is 0.5, and they are saying that along xz plane, this is x, this is y and this is z, along xz plane the hole probes are attached, right? That means a magnetic field direction, and also they are saying that the magnetic field flux density is 0.7 Weber per meter square in z direction. So this is the magnetic field direction, right? So it is you who have to decide which is width, which is thickness. Again they are giving some more information. I is equal to 1 milliampere and it is flowing in x direction. Okay, now we have to calculate hole voltage measured by the probes if the hole coefficient is RH, which is given as 1.25 into 10 raised to minus 3. What is the unit? Meter cube per coulomb. Okay, that is, we have to think, and the thickness is 0.5 millimeter, right, because it is along z direction, it is along the direction in which we are measuring the hole voltage. Okay, so what will be again, again now it is very simple. Once you determine which values to be used, it is RH IB divided by T. Okay, so we can have just the substitution of the values as we have done earlier, and it is 1.75 millivolt. The whole voltage value is very easy to determine, but it is very important to find out which values to be used from the examples, right. We can have the last examples for this chapter, and it is again we are given the electric field EH, that is the whole field. It is 100 watt per meter. In the sample of n-type semiconductor whose whole coefficient RH is minus 0.0125 meter cube per coulomb, right. We have to find out the current density as we have found earlier, and mobility we are given, that is 0.36 meter square per volt into second. RH can be found from this equation 1 over NE. So from that we can find out NE, and substituting the value, the NE can be given as 1 over RH into E. Substituting the value, we can have NE as 5 into 10 raised to 20 per meter cube, right. And we can also have J, the current density, that is sigma E into E. It is actually simply the Ohm's law, right. In the 7th chapter you will learn that Ohm's law has a different form from R is equal to V upon I. We can derive that J is equal to sigma E, and using this equation we can have simple value, we can have simple answer as 2880 ampere per meter square, right. I hope from this examples your knowledge of this chapter has been enhanced from a practical side, and I hope we will meet again with a new chapter. Thank you.